If you're like me, you recognize this toy and its signature rhythmic click-clack noise from dozens of movies and TV shows that you've seen throughout your life. But what you might not realize is that it is also a great demonstration of some basic concepts in physics and mechanics. Welcome back to GSC Go Science Crazy. My name's Jacob, and today we're going to be talking about Newton's Cradle and what happens when you take one of its balls and let it fly. Newton's Cradle is named after Isaac Newton, but not because he invented it. He's only the namesake because his second law of physics is the most famous and simplest way to describe the conservation of momentum that this cradle demonstrates. Newton's second law, commonly written as F equals m times a, predicts the movement of an object in motion. In other words, the net force of an object that is moving is equal to its mass times its acceleration. Momentum, similarly, is a quality of moving matter that is the product of its mass times its velocity. The heavier an object is and the faster that it's moving, the more momentum it'll have. Also, momentum, like velocity, is a vector quantity, meaning that its direction is always implied when it's discussed. With this in mind, Newton's second law can be thought of as the rate of change in an object's momentum being equal to the direction and magnitude of the net force acting on it. In addition to the conservation of momentum, your Newton's Cradle also demonstrates the conservation of energy. This means that energy cannot be created or destroyed. It is always passed on in some way or another. Objects can have two types of energy, potential and kinetic. Kinetic energy is energy that is possessed by an object in motion, while potential energy, on the other hand, is energy that an object stores because of gravity or its own elasticity. And lastly, with that said, in order to understand your Newton's Cradle, you'll also need to know a little bit about collisions and the concept of elasticity. Elasticity refers to an object's ability to deform and spring back to its original shape without losing energy. In the case of collisions between two objects, the collision is considered more elastic the less energy that is lost. This means that perfectly elastic collisions don't exist in the real world, as energy is always lost due to friction. Now that you know a little bit about what's going on in terms of the physics, let's look at how these concepts are demonstrated by your Newton's Cradle. Before you touch the cradle at all, every ball is still and all kinetic energy, potential energy, and momentum are at zero. When you lift up a ball at either end, it gains potential energy from gravity. When you release the ball, this potential energy converts itself into kinetic energy, and it gains momentum the entire time it's in motion. This ball eventually comes to an abrupt stop when it collides with the one at rest. The kinetic energy of the falling ball is conserved by microscopically compressing the ball it collides with. When this ball is compressed, the energy is briefly stored as potential energy until the ball returns to its original shape and passes on kinetic energy to the neighboring ball. Here, conservation of momentum ensures that the energy travels through each ball in the direction of the momentum carried by the original falling ball. This is also why the falling ball comes to a stop against the ball it collides with, instead of bouncing back towards your hand. This process continues down the line until the energy reaches the last ball. Instead of transferring its kinetic energy into a neighboring ball, it swings out and upwards until it is slowed down to a stop at the top of its arc by gravity. This ball then falls back down, collides with its neighbor, and starts the whole process over again in the opposite direction. If this experiment could be done in a frictionless environment with a perfectly built device, this demonstration could go on forever. But since this isn't the case, the balls in your cradle will eventually slow to a halt because their energy is not perfectly conserved within the system. Energy is lost in several ways. When the balls hit, they vibrate, causing the air around them to move in the form of sound waves that you recognize as the signature click-clack noise. Also, friction between the balls when they collide and between the molecules within them as they compress and return to shape converts some of the energy into heat. Over time, these small losses of energy outside of the system slow it all to a halt. This demonstration could also be expanded to explain how mass figures into all of what we've learned. Because the force an object carries is equal to its acceleration times its mass, when you lift up two balls to start the collisions, enough force travels through the system to lift up two balls on the opposite end. This also works when using 3 or even 4 balls to start the collisions. I hope this helped you understand your Newton's Cradle a little bit better. For more fun science experiments and lab supplies, visit us at www.gosciencecrazy.com. Until next time, take care and go science crazy.